Assalamualaikum warahmatullahi wabarakatuh and good day. In this video, we are going to continue with our new topic, diodes. So the content for our lecture for today are going to be we are going to analyze the PN junction and the semiconductor diode. We are going to recognize and familiarize with the diode equation and the IV characteristic, current voltage. And then finally, we are going to apply and analyze various circuit models of the semiconductor diode in simple circuit, half wave rectifier and full wave rectifier. So let's start with introduction on what is the PN junction. So basically, semiconductors are materials that have electrical properties which fall somewhere in between conductors and insulators. For example, let's consider the conductivity of three common materials that we usually see every day: copper, glass, and silicon. So copper is a good conductor. It is being widely used for wire, and the conductivity of a copper is 0.59 exponential 6 Siemens per centimeter. Then we also have a common insulator, which is glass, that range the conductivity in between exponential minus 16 to exponential minus 13, which is very small, Siemens per centimeter. While silicon, a material which is a semiconductor, have a conductivity that varies between exponential minus 8 to exponential minus 1 Siemens per centimeter. So semiconductors technology rarely employs pure or intrinsic semiconductors. In order to control the number of charge carrier in a semiconductor, a process called doping is employed. So the doping process consists of adding impurities to the crystalline structure of the semiconductor. The amount of these impurities is controlled, and then the impurities can be of one of two types. The first elements is to provide impurities called as donors, ataupun penderma, since they donate an additional free electron to the lattice structure. So basically donors, dia akan dermakan dia akan dermakan elektron bebas. Dia ada elektron lebih, jadi dia boleh dermakan. However, an additional hole is created by the doping element, and this is called as the acceptor. Penerima. Ada yang menderma, ada yang menerima. Since it accepts a free electron from the structure, and it's going to generate a hole in doing so. So basically, donors have extra electron, acceptor have extra space or extra hole. Semiconductors which is doped with donor element are going conduct current predominantly by means of the free electrons, and therefore it is called as the N-type semiconductor. N for negative. It have more electron charges, so electron will be negative charge. And then the acceptor element is used as the dopant. Holes constitute the most common carrier, and it is said to be called as the P-type semiconductor. Okay, then we have the PN junction and the semiconductor diode. When a section of P-type materials, the donors, the acceptor, and a section of the N-type materials, the donors, are brought in contact to form a PN junction, a number of interesting properties are going to rise. So the PN junction forms the basis of the semiconductor diode, which is a widely used circuit element. So let's take a look at the structure of a diode itself. So we have the P-type materials, and then we have the N. So the border in the space in between this Pn, okay, is called the depletion region. So this region is a small section where the mobile charge carriers, holes, and free electrons come into contact with each other and it's recombined. So apa yang terjadi di sini adalah elektron yang ekstra di bahagian N akan bergerak ke holes yang terdapat pada bahagian P. Okay, jadi bahagian ini akan mengalami perubahan elektron di mana elektron akan memenuhi sebahagian daripada kawasan P, manakala holes itu akan berpindah, akan sebahagian N ni akan mempunyai beberapa holes. Jadi bahagian ini yang sangat kecil ini dipanggil sebagai depletion region. And the charge separation therefore cause a contact potential to exist at the junction. And this potential is typically on the order of few tenths of a volt and depends on the materials. For silicon, the contact potential is around 0.6 to 0.7 volt. The contact potential is also called as the offset voltage, V gamma. Okay, V gamma. So next we have the symbol or basically the technical symbol for a diode. So the arrow in the circuit symbol for the diode indicates the direction of the current flow. So we are looking at the conventional flow of a current, okay, when the diode is forward biased. So basically when a current is forward biased, we are going to assume that the current flow from positive to negative. Okay, but basically if we look based on the movement of the electron itself, ataupun kita panggil pergerakan arah pergerakan elektron akan bergerak daripada negatif pergi ke positif. Okay, dia akan memenuhi negatif dan positif. But we are going to stick with the conventional current flow, okay, where the current flow from the positive to the negative. So basically the negative part is the N and the positive part is the P. Then we have a figure, okay, where this figure show the IV, the current and voltage curve of a diode. So if we look here, we have the current stay zero from voltage 0 until a certain part around 0.6 to 0.7, where it suddenly exponentially rise, okay, and this is where we call the contact potential or the offset voltage. Okay, for this diode, we can say that the offset voltage is between 0.6 to 0.7. Okay, next we also have a phenomenon called as the Zener breakdown. This is related to the avalanche breakdown. It is usually achieved by the means of heavily doped regions in the neighborhood of the metal semiconductor junction. The high density of charge carrier provide the means for a substantial reverse breakdown current to be sustained at a nearly constant reverse bias. So we are going to have the Zener voltage called as Vz. So to summarize the behavior of the semiconductor diode, it is useful to refer to this figure here. So we have IV characteristic of a semiconductor diode. So the previous graph show from 0 to a positive part where we have understand about the forward bias region. So forward bias region is when the electron move from N to P. Okay, it move forward. And then we have the depletion region, okay, where we call as V gamma. And when we observe this figure, we are going to see that when the voltage across the diode Vd is greater than the offset voltage, the V gamma, okay, the diode is said to be forward biased. Okay, so electron are going to be energized and it can move from N to P, from the donors to the acceptor. and this acts similar to as a short circuit, and current conducted, okay, in this part, in the forward bias region. But when VD, okay, the voltage D is in between V gamma and the Zener breakdown voltage VZ. The diode acts very much like an open circuit. Okay, open circuit means no current is flowing, and it's going to conduct a very small reverse current I0, and the value of the I0 are going to be very small in nanoamperes unit. And finally, so this is the reverse bias region. Okay, so the next part we have the reverse breakdown region. And finally, if the voltage VD is more negative than the Zener voltage VZ, okay, it is smaller than negative VZ, then the diodes are going to conduct the electric again. Okay, the currents are going to flow again, and but this time it is in reverse direction. Okay, reverse direction. Okay, next we are going to apply and analyze various circuit models of the semiconductor diode. So we are going to have a simple circuit, we are going to have half wave rectifier, and we are going to have last one, full wave rectifier circuit. So basically the half wave and full wave rectifier circuit, uh, we have a specific lab for that, and I believe everyone had done the lab. Okay, so this is a typical diodes. Okay, so you can see here it is being remarked as A and K. So A is for anode and K is for cathode, or CATHODE. Okay, so anode is the positive terminal and cathode is going to be the negative terminal. So this is positive and this is negative. And how can we distinguish between anode and cathode? But just by looking at the physical diode itself. So basically we can refer for this kind of diode. Okay, so for this kind of diode, okay, so the stripe at one ends are going to be the negative terminal or the cathode. Then we have diode limiting and clamping circuits. So this is the first part. We are going to learn about diode limiters and diode clampers. So let's start with so basically diode limiters are sometimes used to clip off portion of signal voltages above or below a certain level. So we want to clip, or we want to cut the voltage. Then the other one, the clamper, is used to add or restore a direct current level to an electrical signal. So we are going to start with diode limiters. So diode limiter, which is also called as the clipper, is used to limit or clip the input voltage to a certain level. So we have maybe you have heard about hair clipper, hair trimmer. So diode limiter is having like a trimmer, okay, a clipper where it's going to cut uh, any unneeded voltage, okay, for that circuit. And the output voltage can be determined by the voltage divider R1 and the load resistor RL. So let's say we have a circuit, so we have the diode is in parallel with the resistive with the load resistor RL. We have R1. So the V out, the output voltage, are going to be equal to RL over R1 plus RL times V in, okay, the input voltage. Okay, limiting of the positive alternation. In this circuit, okay, the diode is going to be forward bias when the input voltage is in the positive alternation in this part. So the currents are going to flow, but it will be limited to 0.7 volt. Okay, but when the input voltage is in negative alternation, okay, in this part. So the current are going to flow in reverse directions. So it will not pass the diode, but it will flow through the load resistor, and basically we are going to have the output voltage and the input voltage is going to be the same. Okay, it will not be limited or clipped. Next, if we want to limit the negative alternation, okay, we can easily do so by changing the direction of the diode. Okay, this time when when the input voltage is in positive alternation, okay, it will flow. It will not. Okay, it will not flow through the diode, but it will flow through the load resistor, and therefore we have the output voltage and the input voltage is the same. But when the input voltage is in negative alternation, okay, negative di sini, okay, this time the current are going to flow in this direction. It will flow through the diode, and the diode basically are going to clip the voltage to only 0.7 volt. So remember that in a parallel circuit, okay, the voltage between the diode and the voltage between the load resistor are going to be the same. Okay, are going to be the same. Okay, so let's take a look at one example. So the question is, what would you expect to see displayed on an oscilloscope connected across RL? Okay, connected with cross RL. We put the oscilloscope here in parallel with the load resistor and the diode 1N4001, and in the limitation in figure 235 here. Okay, so we have the input voltage is sinusoidal AC. So the peak current is 10 volt minus 10 volt. We have R1 100 ohm and RL 1 kilo ohm. So we can see that the diode is forward bias. Okay, the diode is forward bias, and this diode are going to conduct um, the input voltage when the input voltage goes below minus 0.7 volt. Okay, so and right here equal to negative 0.7 volt. And for the negative limiter, we are going to determine the peak output voltage across RL. Okay, the peak output voltage by the following equation. We have the equation V, so we can substitute the value from the equation. So 1 kilo ohm divided by 1.1 kilo ohm times the peak voltage. The peak input voltage are going to be 10 volt. So this is going to be equal to 9.09 volt. So what we are going to have is a graph. Okay, we are going to have the output voltage V out from 0, and it is being limited at the negative. So what we have here is the value here are going to be negative 0.7 volt, while the peak voltage are going to be plus 9. Okay, next, the bias limiters. The level to which an AC voltage is limited can be adjusted by adding bias voltage V bias, and we are going to add V bias in series with the diode. So there will be two types of bias limiters. One is a positive and another one is negative limiter. So this is a circuit for a positive limiter, okay, with V bias. So as you can see here, okay, the diode is being used to limit the positive alternation, and we put V bias uh, to add 0 to add with the voltage during the positive alternation. And then we have the other circuit, okay, where this is a negative limiter, and we have the V bias is also in series with the diode. Okay, so by turning the diode around, the positive limiter can be modified to limit the output voltage to the portion of the input voltage waveform above V bias minus 0.7 volt. So we can change, okay, the diode, and basically we are going to get the output voltage are going to be V bias minus 0.7 volt. Okay. And similarly, we can do the same for the negative limiter, okay, to limit the output voltage to the portion of the input voltage waveform below. So it will be negative V bias plus 0.7 volt. Okay. So we can see the difference here and here. So let's take a look at one example. In this figure, it showed a circuit combining a positive limiter with a negative limiter. So positive limiter D1 and negative limiter D2. And we need to determine the output voltage waveform. So we have the peak input voltage is 10 volt, R1 1 kilo ohm, V bias is 5 volt for the negative and the positive 5 volt. So the solution is when the voltage at point A reaches positive 5.7 volt, okay, the diode D1 are going to conduct and limit the waveform to only 5.7 volt, not more than that. And then this is during the positive alternation. Okay, then diode D2 will not conduct. Okay, diode D2 will not conduct any current until the voltage reach negative 5.7 volt. Okay, therefore positive voltage above 5.7 volt and the negative voltage below negative 5.7 volt are going to be clip off. So the result is going to be shown in this figure here. So how did we get 5.7? So easily 5 volt, okay, of the V bias plus the offset voltage of the diode 0.7 volt. So we are going to get 5.7 positive and negative 5.7. Okay, next, the voltage divider bias. The bias voltage sources can be replaced by a resistive voltage divider in order to illustrate the basic operation of the diode limiters. So the bias voltage is set by resistor value according to the voltage divider formula. So if you still remember the voltage divider formula in the resistor topic, V bias is equal to R3 over R2 plus R3 V supply. So let's take a look at some example of diode limiters with voltage divider bias. So we have a positive limiter, okay, where the diode is connected in between R2 and R3, and we have a positive V supply. Okay, then we have a negative limiter. The difference is just the negative V supply, so we have a negative. And the other one, we have a variable positive limiter. Okay, let's take a look at one example of output voltage waveform. So we have a circuit. The input voltage have the peak voltage 18 and minus 18. R1 10 kilo ohm. We have a positive V supply 12 volt. R2 100 ohm, R3 220 ohm, and we have diode 1N4001. So we can see that this is a circuit of a positive limiter, and then if we use the equation of voltage divider formula, we are going to find that V bias is equal to R3 over R2 plus R3 V supply. Okay, R3 is 220 over 100 plus 220 ohm times the V supply 12 volt, and we are going to get V bias equal to 8.25 volt, and therefore the output voltage waveform are going to be shown like this. So we have the V bias 8.25 plus the offset voltage 0.7, and we should get uh, during the positive alternation. Okay, during the positive alternation here, um, the voltage are going to be clipped at 8.95 volt. Okay, and the positive, so this is for the positive part, and then the negative part, it will be the same like the input voltage, where it's going to peak at negative 18 volt. Next, diode clampers. So a clamper adds a DC level to an AC voltage. Clampers are sometimes known as the DC restorer. Okay. And there are positive clamper operation and negative clamper operation. So um, similar like the limiter. So we have a clamper with positive and negative. So this is a positive clamper operation. So basically what we have is, in the circuit we have the AC input, okay, we have the diode, and we have the load resistor, but this time we also have a capacitor. So we have a capacitor. So the input voltage is sinusoidal, as you can see here. When the input voltage initially goes negative, okay, in this part negative, the diode is going to be forward bias. Okay, it's going to be forward bias. Akan mengalir macam ni, forward bias. And this is going to allow the capacitor to charge to near the peak of the input. So capacitor are going to charge, it will store electron, where the peak of the input are going to be Vp in, okay, the peak voltage input, okay, minus 0.7 volt, which is the offset voltage of the diode. And just after the negative peak, okay, just after this peak here, okay, the diode is going to be reverse bias. So it's going to be reverse bias, and this time, during this time, the capacitor will not charge any electron anymore, but it's going to discharge. And the capacitor will this capacitor can only discharge through the high resistance of RL, okay, during this part. So it's going to discharge through the RL. The current cannot flow in the reverse bias diode. So from the peak of one negative half cycle to the next half cycle, the capacitor are going to discharge very little, and the amount that is discharged depends on the value of RL, and therefore we are going to get the output voltage is shown here. So V out are going to be Vp in minus 0.7 volt. Okay, it's going to move here, and the net effect of the clamping action is that the capacitor retains a charge approximately equal to the peak value of the input less the diode drop. Okay. And the capacitor voltage acts essentially as a battery in series with the input voltage. So dia macam bateri lah sekali dengan input voltage ni. And DC voltage of the capacitor adds to the input voltage by superposition. So the DC voltage of the capacitor dia akan supply masa positive alternation, and it will add up, okay, the distance here by the value of the capacitor's charge. Okay. So let's say if the diode is turned around, so we are going to have a negative DC voltage is added to the input voltage, and this is going to produce the output voltage, okay, at a value of negative Vp in plus 0.7 volt. So this is for a negative clamper operation.